Okay, this is a continuation of the 6.2 notes. Last time in class we started, I believe it was example 4. I'm going to go ahead and rework it just because we were rushed for time, and I'm going to remind you about the fundamental identities. The first ones we already talked about just when we defined our trig functions. We said that cosecant is the reciprocal of sine, so that's why this is 1 over sine theta. Secant is the reciprocal of cosine, and cotangent is the reciprocal of tangent. The next two were ones that we hadn't talked about yet, but that you need to memorize. Tangent theta is actually sine over cosine, so cotangent would then be the opposite. It's cosine over sine. And then the last piece is the Pythagorean identities. Sine squared theta plus cosine squared theta equals 1, and then the other two are found by dividing this one by either sine or cosine squared all the way across. So that's how they came up with the other versions that have tangent secant and cotangent cosecant. Now, why do we care about these? Later on we'll kind of prove some of these identities, but right now we're going to use them to help us simplify things or write one trig function in terms of another. So this first one is the one we did in class together, but I'm going to go ahead and redo it so we can discuss it a little bit more in detail. The description says let theta be an acute angle. Now that tells us some things about our angle, which will help us figure out something about the end of the problem. It says express sine theta in terms of cosine. So that means our final answer should be sine, went backwards. Our final answer should be sine theta equals something with a bunch of cosines over here. Okay, so the only property that I know of from the other page that has sine and cosine together and nothing else was the one that said sine squared theta plus cosine squared theta equals 1. That was the Pythagorean identity. So we want to have sine be the part we solved for. So we're going to subtract the cosine squared over, which would make this 1 minus cosine squared theta. And then we need to get rid of this squared part. So we're going to take a square root of both sides. Now anytime you take a square root, unless you know for sure what the sign is, you're supposed to write plus or minus. Also, I didn't talk about this in class, but make sure you don't try to cancel the square root with this piece. If you have a binomial, you cannot do that. It would have to be a singular term to be able to cancel that, or a binomial squared. So that does not cancel out that cosine squared. Okay, so my next step is to discuss how do I know which of these signs is the answer, or if both of them are the answer. So that goes back to this being an acute angle. If an angle is acute, it is in quadrant 1. Okay? So think about if you drew a triangle in quadrant 1. This would be your theta. This would be opposite. This would be adjacent. And the hypotenuse, of course, is the length going from the origin to the point out in space. So because in this space, sine is opposite over hypotenuse, in this situation, y's are going up, so those are positive, and this distance is also always positive. So that is why we know that sine theta is greater than 0 for all acute angles. So then that means that this doesn't need both the plus and minus, it just needs the plus. And we don't typically write the plus. We just leave it as a square root and assume that everyone knows that without a sign in front, it is a positive square root. Or we also call that the principal square root. Okay, so that one a little bit slowed down. I know we went through it kind of fast in class. So let's talk about B part, which is express tan theta in terms of sine theta. So let's think about one of the formulas from the other page that used tan and sine. The one that popped into my head was just the one in the second group, which was tan theta equals sine theta over cosine theta. Now the problem is we want tan to be in terms of sine only. So if we could somehow get cosine theta to turn into something with sine, then we would be able to say, oh, okay, well this is then all sines. So again, let's go back to that sine theta squared plus cosine theta squared. And notice when we square these, we write it on the actual trig function, not on the angle. You can also write this. It's just not very common to see people write that. And then this equals 1. So this time I am going to solve for cosine so that I can replace the cosine down here. So cosine squared theta would be 1 minus sine squared theta. And we would take the square root of both sides. Write our plus or minus in. And then again, we would think about if this is an acute angle, then we know that any acute angle, this is the adjacent side, we would have adjacent over hypotenuse. So we're saying that those are both also positive measures. Now the only thing that's a problem here is that cosine theta is undefined at certain values, so we have to make sure that our theta is bigger than 0 but less than 90 degrees, which is pi over 2. Because if you have adjacent over hypotenuse for certain angles, that's not going to work out. So for us, we have to keep our theta in this region but not actually on the axes. So, and that has to do with the tangent really more than the cosine, and it's because cosine is in the denominator of this ratio. So when we rewrite this, this would be tan theta of sine theta over the square root of 1 minus sine, oh I forgot my squared on this one, sine squared theta. And in this case, this is one of those where we wouldn't rationalize it, because why would you go through the bother? It's nasty to rationalize this because it has trig functions involved. So sometimes you'll even notice that even though we rationalize a lot of things, they'll ignore it in certain situations because it just makes it messier. Okay. So then we want to look at this example 5. I wanted to at least do a couple of these before we came back to class on Monday. Let me delete out those extra marks. Okay. So this one says the fundamental identities are often used to simplify expressions involving trig functions. So show that the following equation is an identity by transforming the left side into the right side. So essentially we will not even look at writing the right side. We're just going to start with what we have on the left. And we're going to use as many things that we can think of using our 3 different identities that we learned, and we're going to see what we can transform this into. A good place to start is if your final answer is a sine or a cosine, you probably want everything in your problem to be in terms of sine or cosine. So if you think about it, secant theta, this is using our reciprocal identity, is 1 over cosine theta. So I could replace that as, let's just do it over here. That would be 1 over cosine theta, and tangent theta, this is the second identity from the chart, is sine theta over cosine theta. Okay, so that's good because we're going to get a common denominator by doing these two, cosine. And then we still have this parentheses of 1 minus sine theta, which we'll worry about in a minute. Okay, so since these are both cosine in the denominator, we can add this together. This is 1 plus sine theta over cosine theta times 1 minus sine theta, and maybe I want to think of this as a fraction, over 1. Now I can multiply top times top and bottom times bottom. Okay, so this is FOIL, so 1 times 1 is 1. 1 times negative sine theta is negative sine theta. Sine theta times 1 is positive sine theta. Positive sine theta times negative sine theta is negative sine theta squared. The bottom is just cosine times 1, so that would just be cosine theta. Notice that there are like terms on the top that cancel. They're both cosine or sine thetas. One is positive and one is negative. So that leaves me as 1 minus sine squared theta on top. And this is where our final identity comes into play, because we had a rule that said sine squared theta plus cosine squared theta equals 1. That was our Pythagorean identity. If you solve that for cosine squared theta, that is 1 minus sine squared theta. That's our numerator, so that means our numerator is actually cosine squared. And when you have something on top with something on bottom that matches, essentially, remember this is squared, one of each of those will cancel out. So you're just left with cosine theta. So that is how you can use the three identities, the reciprocal, the tangent and cotangent ratios, and the Pythagorean theorem identities for trig functions to take something that doesn't look like another side, and you can actually do some substitutions, simplify using algebra, and you can get it to turn out to be something more simplistic. So that now is a fact for us, that secant theta plus tangent theta times 1 minus sine theta will always be the same value as the cosine of that angle. So just something interesting, not something that you would think would happen, but that's what's cool about being able to play around with these identities. So I actually want to do another video on 6.2, but I'm restricted on time for each video, so I'm going to stop here, and I'll make a part 2 that talks about a little bit about how this is going to connect eventually to the unit circle. And then once I do that, we'll be in a good place to start for class on Monday.